Welcome everybody in the lecture hall. Welcome everybody joining us on Zoom. Welcome everybody watching us from the future, binge watching for the exam. What's on the menu today? So we are going to finish that part on the data models. We are then going to start looking at MapReduce. So at last, we start to actually query data, which is the whole point of everything that we are doing. But before we start, I have two questions for you. And this is the first one. So in HBase, where are the key values stored? So you remember the key values are these atoms in HBase, right? It's when you have a specific row ID, a specific column family and name, and a specific version that gives you a key value, which is what is stored physically in the persistence layer. And so I'm asking, what are all the places that key values are stored? Only on disk as immutable file structures, or on disk in immutable file structures, as well as in a write-ahead log and in memory, both in the mem store and in caches, or in memory only for fast retrieval and in the CPU L2 cache, or on disk in a write-ahead log and on memory for fast retrieval. All the places. Oh, wow. That's so great. You follow everything 100%. Indeed, absolutely. It is stored on disk. That's these H files, right? Where we have sorted lists of key values together with some index to find them faster. Also in the write-ahead log, you remember the write-ahead log is this protection against a big crash where we suddenly lose all the data and the memory is basically failing us. So all the fresh key values in memories would be lost. And the write-ahead log is a precaution, an extra precaution that we take, that before we put any of these in memory, we put them in a log. And the log is appending. So the difference between the write-ahead log and the H files is that in the write-ahead log, it's in the order of arrival, right? In the order in which they have been added to the system. While in the mem store and in the caches, it's started by a key, right? It's a lexicographic order there. All right, perfect. So you're doing well. It's really great. And so I have the other question for you. Is this document well-formed only, valid only, well-formed and valid, or neither of those? This question makes sure you understand what well-formedness means, what validity means, and the difference between the two. Let's see if we get 100% on that one too. Oh. Okay. So it's supposed to be well-formed, but now, why do people say neither of those? Is there a typo or something? I don't think so. I've asked this question for many years. So it's well-formed, right? So if you put that in a parser, like in Oxygen, it will be nicely colored and syntax highlighted and accepted by the parser. And this is what we call well-formed. It means you can successfully parse it and build a tree in the memory. That's what well-formed means. Validity is something difference. That is something that comes after well-formedness. Validity is when you want to enforce specific structures. You want to say, I want very specific elements, I want them to have very specific children, I want attributes to have very specific types. This is validation. Why is this document, why can we not say that this document is valid? Anybody? Exactly, we have no schema. So if you have no schema, you cannot say anything about validity. That's another difference with well-formedness and validity. Well-formedness, if you ask for XML well-formedness, that's yes, no, right? It's an absolute thing to ask. You still need to say if you mean XML or JSON, of course, but it's an absolute thing to ask. Validity indeed depends on the schema. You could have a schema against which the document is valid and another schema against which the document is valid. If you don't specify any schema, then of course you cannot say the document is valid. That doesn't make sense, right? All right. Those who answered neither of those, if you find a typo or anything, let me know, but I really think there should be none in there because it was specifically syntax highlighted by oxygen, so normally it's well formed. Okay. So that brings us back to data models. So to recap, we saw that it is possible after you have checked that a document is well formed, after having parsed it and after having built the tree in the memory, then you can start asking whether or not that document follows specific structures. These specific structures can be enforced with a schema. And I gave you one example last week of a schema language that is known as JSONs, because for teaching, it's actually good because the schema is also JSON and it looks very much like the instance, right? So it's very intuitive. And then I told you that there are other technologies out there. In the case of JSON, we have JSON schema, that is the most popular schema language. And for XML, we have, guess what, XML schema, right? Which is also the most popular schema language. It's not the only one. There's also RelaxNG or Relaxing, I'm not sure how to pronounce, Schematron and others. So there's other ways that you can specify schemas for XML, but there's plenty out there. And you had the exercises. Who did the exercises? Who has not looked at the exercises yet? Right? You should. So the exercises give you a lot of instances and schemas that you can work on, and that is really the best way to learn specifically how JSON schema and XML schema actually work. So what I would like you to do is to make sure that you read the textbook. Who read already the textbook, the chapter on data models validation? Okay, so if you haven't done so, please do read the textbook. There's many explanations on XML schema and JSON schema, and I will give it to you as a self-study, right? Because it's really very, you need to go through every one of the feature and learn them and solve the exercises. Really, it's the best way. You should download Oxygen from the IT shop. It's free for all students at ETH, and use it. That's the best way you can get the hang of it, right? So self-study. And today I would like to focus on understanding, on giving you the high-level picture on how schemas fit with data frames and how it all orchestrates together. The logic behind it, actually, in the big picture at ETH, have you heard of Packet? Who heard of Packet? Okay. So this is something that's going to change at ETH in 2027. There's going to be a few things like there's going to be more free time for the students, more care about the workload of the students, and so on. And there is also a general shift that is already starting to happen today in the teaching, which is trying to throw less knowledge at people. Like, for example, when I showed you XML, JSON, can be, a bit long, right, to go through that knowledge. And we try now to try to switch to focusing on the understanding, just not throwing knowledge, but really make sure you understand. And I had a high school teacher that I still remember today. She was telling us she doesn't want us to learn by heart. She wanted us to understand by heart. And there is a subtlety here, because it's not about knowing everything by heart, every single word and so on, because then there is a danger that it's mechanical, right? You learn by heart sentences, then you just reproduce. But understand what is going on. And that's really what I would like to do here. So I'm going to spend time on these data frames to explain to you how this fits with schema validation, right? Okay. So on the left, you have something that you're already familiar with from last week. That's JSON. It basically specifies a constraint on an object, says that an ID, a key that has the name ID should be an integer, should be associated with an integer. If there is a key called name, it should be associated with a string. And if there is a key called living, it should be associated with a Boolean, right? You remember that they are optional, right? By default, the keys could be missing, but if they are there, then they need to be an integer, a string, a Boolean. We also saw in the compact syntax that you cannot have extra keys, right? With this schema, so it wouldn't be allowed to have a key that is not one of these three. You could change the schema to allow for that, but then it's more involved, and with the verbose syntax, you will see in the exercises how to do it with JSON schema to allow for extra keys. But here they are not allowed. So you can only have ID, name, and living. Now, what I would like you to do is imagine that you have a very large collection of objects that are valid against that schema. Let's say millions of them, millions of objects. They are all not only well-formed, JSON, but also valid against that schema right here. Imagine these objects, millions of them. Who already sees that you can visualize these millions of objects as a table with 3 columns like this? Who sees that? Right? Something intuitive, right? You have millions of objects. They all have these 3 keys, potentially absent, right? Could need not there, but they have all these 3 keys, and every ID is an integer. So you probably have the visual that you see on the right? Since every ID is an integer, then here you have a column full of integers. Here you have a column full of strings, right? The name and living, these are Booleans. So the key part to understand is that when you have such a collection of valid JSON objects, you can view them as a relational table, right? That is the key point. Now a few comments here. In a relational table, it's allowed to have nulls, right? You can have nulls in some of the places, in some of the cells. There's many ways to interpret that, but most commonly, null is the absence of value. So even if ID were missing, or name were missing, or living were missing, you would just have a null in the table at that place, and that would be fine. So that would still work, right? So this specific schema, if you have a huge collection, not necessarily huge, but also huge collection of JSON objects valid against it, then you can equivalently visualize this data with the table that you see on the right. Now, that would not work with all schemas. It might be generally that some schemas do not allow you to do that, but I will show you that there's actually a lot of schemas that allow you to do that kind of things. We will also see that while in this case, we get a relational table, that will not necessarily always be a relational table. It might still be something we can visualize, but it could not be a relational table, right? Who could give me an example of why we might not have a relational table? What kind of schema? If you don't know, I will show you. Don't worry, I have slides for that. All right. So here's an example of the sort of things where that's no longer a relational table. So I slightly adapted the schema, and now I have, instead of the name being a string, now name is an array of strings. Can be 0, 1, 2, 3, 10, but it's an array of strings. It turns out that I can still visualize that. I can still visualize that because then what I can do for all of my strings that are in there, I can just stack them, right? So here, that is the first JSON object, and then I can just stack all of my strings that are part of name, right? Potentially empty, right, if the array is empty. So I can visualize it in this way. Who sees that? That if I have a very big collection of objects valid against that, that's how I can visualize them. Who sees that? Just to make sure everybody's on board? Yeah? All right, perfect. Now, this is no longer a relational table. It's no longer a relational table. Are we breaking relational integrity or domain integrity or atomic integrity here? Who thinks we have relational integrity? We do, right? We do have relational integrity because here there's ID, name, living. It's all in there. Who thinks we have domain integrity? We do also, right? Because every ID is an integer, every name is an array of strings, and every living is a Boolean. So we have also domain integrity. Who thinks we have atomic integrity? Who thinks we do not have atomic integrity? And you're right about it. We don't. This is the one thing we're breaking here. I told you we would be breaking rules in big data for engineers. And we are breaking a rule here, one of these rules. So we do not have atomic integrity. And the way you see that is basically that this line doesn't go all the way through, right? So you basically have here some nested structure, but it's not going on the entire line. And what we have here is no longer a relational table, and we call that a data frame. Who has already heard of data frames? Many people, right? It's a buzzword with pandas and all these things. Well, it turns out, now that's the insight here, that a data frame can be seen as some sort of generalization of a relational table that also allows for breaking a few rules. You can break atomic integrity. And what we see here is that a data frame is basically a collection of valid JSON documents, right? So think about this, maybe also offline. A data frame can be seen as a collection of valid JSON documents, okay? There are a few constraints on the schema for it to be possible to have a data frame. Let me tell you one example of something that would not work anymore with data frames. Imagine that I have a schema in JSON schema or in JSON that allows me to have extra keys that are not in the schema, right? That's what we call an open object type, right? So imagine that you allow for extra keys arbitrarily. Who agrees that's not a data frame anymore that we have then? Who sees that? Because in a data frame, you have specific columns, right? So if you now allow for extra keys, what do you do with them? Where do you put them, right? So in a data frame, you need to know in advance the columns that you have. So that sort of schemas wouldn't work. So it's not all of them, but many of them. Okay, here's another one that is a schema that fits in a data frame. Now, name is no longer an array of strings, but it's a nested object with first and last. And see how we can visualize it in the data frame now. I have these subheaders somehow here, first and last, that are below name here. And now I have my subcolon sort of with the first names and my subcolon with the last names, right? Who sees the correspondence between the two? Right, very good. It's very important to visualize this. It's absolutely crucial, okay? Now, I'm going to push you a little bit. What about this? It's a bit subtle. I changed something. Now, I have an array combining them, combining arrays and objects. So I have an array of objects.
Sorry,
So
there is a question on Zoom.
Yeah.
So the question is whether, could we not add the column that we need and just put null for all the entries that do not have this column?
Yes, this is true. I'm just wondering if I intended to explain it a bit later. Let me answer now to this question on Zoom. So it is true that technically, if I give you a collection of objects, millions of objects, and the schema is open, it's an open object type, meaning that you can have any keys you want, and the collection has extra keys that are not in the schema, then you are correct that you could draw a data frame by finding all of these keys that are not in the schema and adding them as columns to the data frames and adding nulls everywhere. You can absolutely do that. What's important to see is that in order to draw the skeleton of the data frame, you have to look at the data. The schema is not enough. You have to look at the data, discover these extra keys, and then add the columns. And this is the key part here, is that we do not like that. So in data frames, the schema of the data frame is supposed to be known in advance. Right? So you define, like we'll see in Spark when we actually get to data frames in Spark. So you really have to define that ID is an integer, who dot name, who is a struct, so an object, name is a string, type is a string, and living is a Boolean. And so you do not want to have to look at the data to discover the keys. So that is one of the differences. Right? Does it make sense? Right? You understand that if there's extra keys, we are obligated to look at the data to know which ones. Right? We cannot just look at the schema. So that's the first thing. The second thing, and this is why I wanted to only explain it later, but since you asked the question, I'm going to tell you. We will see that when we have a collection of JSON objects like this that is valid against a schema, and this is a schema that is compatible with data frames, there is a much more efficient way to store that data than as JSON. Right? JSON is verbose. You keep repeating the keys all over the place, so you probably saw that, right? But if you can actually fit your data in a data frame like this, then you can save that in a different format that's not JSON. An example of format is Parquet. And that format is highly optimized for the data frame structure. And in that format, what you typically find is a schema, a data frame schema. It actually looks pretty similar to a JSON schema, just not using that syntax. But you have basically the data frame schemas that tells you the columns in the data frame and the types of the columns. And then once you have the schema, the format in which you can store the data is very efficient because you only need to put the values. Because you know what columns these are. So you just say one Albert, first Einstein, last false, and so on. So you basically can store it in an optimized way. And one of the ways you save space is you do not repeat the keys anymore, as you would do in JSON. Who sees that? Who agrees that if I store that data as JSON, we keep repeating the keys all over again in every object, right? That you see. And if we see it as a data frame, we no longer need to do that because it's always the same keys, always and always and always, right? So it's more efficient. So that's the second reason. To have a data frame, we need to be able to define a schema, and we need to know in advance all of the keys that they are going to be. We cannot allow for any unexpected key, because the moment you want to save the data, you're going to have a problem if there's extra columns. Did I answer your question?
Yes. Yeah,
thank you. Awesome. I intended to explain that a bit later, but now it's done. So I have already done that. Okay. Okay, so I'm now just continuing to push you. So now I'm mixing the two. I both have a nested array of nested objects. And now you see I did the two things. I both have these lines that don't go all the way through because it's a nested array. And at the same time, I have these subcolumns, these subheaders here that look like this. Who agrees that this schema, a collection of JSON documents with this schema, would fit in a data frame that looks like this? Who sees that? Right? Okay, very good. And now I'm going to show you something disturbing. It's that this other schema that is different, technically you could get the same visual. Name is an array of strings, type is an array of strings, and you see, you kind of get the same data frame. It's just that you don't think of the columns and rows in the same way. Is that if you have name as an array of string, then you basically see like this, Albert Einstein and first last. But if you see instead an array of objects with name and type, then you see it like this, Albert first and Einstein fast. So it's two ways of looking at this. In fact, this is something that people are aware of, that these two schemas are kind of dual of each other. Right? It's two different ways of storing the same data. And in fact, we see it in practice. Like, for example, we worked with people at CERN on high energy physics, and they store the data in something that looks like that, all of the collision data at CERN, and then they analyze the data to try to find the Higgs bosons or such particles. And in fact, they do store originally the data like this. And then one of the tricks that you can do to optimize the querying is to transform the data to make it look like this, which is more efficient for querying. So this is something you do see in practice, these two. But there is a subtle difference, is that here, you basically have always a pair of name and type, but here the two arrays could have different length. So you could have, for example, 10 names and 5 types, right? Okay. All right, so these are the data frames. And now that we have the data frames, I already talked a little bit about that, but I can talk about data formats, because it turns out that XML, JSON, CSV are not the only formats out there. There's plenty of other data formats that you can have. And so the way to formally think of this is that you need to decouple the format from the data model. From a data model perspective, a data set is often a list of maps. It's a very formal and fancy way to say that. The maps are basically the JSON objects, and the lists are basically the collections, right? Even a table is a list of maps, right? It's a list of records. So from an abstract perspective, a data set is a list of maps. And when you look at this list of maps, there are a few constraints that may or may not be there, and that has to do with relational integrity, atomic integrity, and domain integrity. First, sometimes the maps are flat and sometimes they are not. So on the left, you have a flat data set, and on the right, a nested data set. And now I represent them as data frames because you've seen what a data frame is. So flat, nested. These are two different kinds of data sets. That's what it looks like in JSON, by the way. So that's the data frame visualization. That would be the JSON visualization. You see here the keys that repeat. ID, name, living, that's a waste of space here, right, to repeat the keys all over the place. So on the left, it's flat because all of the values are atomic values. And on the left, it's nested because you have nested arrays and nested objects. Okay. Second, you also have some data sets that are homogeneous and some data sets that are heterogeneous because there might be missing values, right? So in JSON, you can just see it because some of the keys could be missing. You see that on the left, the homogeneous one, all the keys are here. You could add the exclamation marks if you want to require them in the schema. And in the heterogeneous data set, some of the keys are missing. These heterogeneous data sets may or may not be data frames. That's what I explained earlier. If you have a schema that already knows of all of these columns, but the keys are optional, then that's a data frame, right? You just have nulls in there, it's still a data frame. If, however, you have open object types and you can have any possible key, and you don't know them in advance, then that's not a data frame. Okay, and that would be the JSON, all right? And now if we mix the two, on the left, I have a flat homogeneous data set that you already know as a relational table, basically on the left. And on the right, we have a nested heterogeneous data set. And this is basically the jungle. You don't even need a schema for that. You can just have a list of objects. They don't even need to be valid against anything, right? Okay. And that would be, you see in JSON, you can handle it all. It's flat homogeneous, you can do it in JSON. Nested heterogeneous, you can handle it in JSON as well. And what I said for JSON is also true for XML, right? You can also do the same kind of things with XML. I will just not do it, but you could also store XML in tables if it has enough structures. Just is a bit more complicated to map. And so, because we have this diversity of visuals and of models, we have plenty of formats that we can save the data to. And this is the daily life of data scientists, right? So JSON, you know now, XML, you know, CSV, you know, that's tables. YAML, I just briefly mentioned that it exists, very similar to JSON in the structure, but different syntax. Data frames, that is a memory representation. That's when you have valid JSON, basically, you can represent it. Then there's libraries for machine learning, libsvm, Parquet is a data format that basically persists data frames to disk. It's a very efficient way of storing valid JSON. Avro is another one. And protocol buffer is yet another technology that comes from Google with also the same idea that you have a schema and then the data is valid against that schema and you can efficiently store it to disk. So a bit similar between protocol buffers and Parquet in this way of doing it. And so every time you need to pick a schema for your data, you should ask yourself, is it nested, is it flat? Because that makes a difference. For example, CSV, you can only use if it's flat. If it's nested, you cannot use CSV. Do you want a text format or a binary format? Generally, a binary format is going to be much quicker to read, first because it's less data, and because it's more optimized and compressed. So you have to ask yourself the question, but you don't always have that luxury, right? If it's JSON that is invalid and a huge mess, then you don't have much choice. You just have to keep it as JSON. But if it turns out that your JSON is very highly structured and there is a schema and everything is valid against that schema, then it's a very good idea as a data scientist to convert the data to Parquet. So to validate the data and then create a Parquet file and then query that Parquet file instead of the JSON file. And the reason is it's going to be faster to open that file and read that file. And another aspect is the schema required or optional? Because if you don't have a schema at all, you don't have much choice. Should be YAML, JSON, XML. But if you do have a schema, then suddenly you have many other formats that you can use, like protocol buffers, Parquet, Avro, and so on. Okay. I'm almost done. What I want to show you now is not just yet another thing to learn. No, that's to make you feel good. Because I told you that last week I gave you a very generic introduction to data types in schemas, and I told you that's universal. The names might change, but it's universal. And just so you see, these are the atomic types in Parquet. I don't want you to learn them, but what I want you to see is the kinds of types you have are not surprising. This is always the same kinds of types. You see, we have Booleans, we have numbers, we have strings, we have binary data, we have dates. There is absolutely nothing surprising in there. So if there's any technology like Parquet, Avro, and so on, you just open the documentation, look at the data types, and you immediately see how it maps to the knowledge you already have, right? So this is the in general. And it doesn't matter how it's called. You just read the documentation and take the names from the documentation. Right. The same goes for the structured types in Parquet, lists and maps. Also no surprise here, lists are just arrays, maps are just objects. They're just called differently. And the same would happen if you look at Avro, if you look at protocol buffers, you will see it's always the same thing, it's always the same kinds of types, just with different names. That's protocol buffers, by the way. So you see, you shouldn't be surprised here. It's a different syntax, it's different names, but look, it still looks like a JSON object, right? The schema for a JSON object. We have a string that is required, string repeated, that's basically an array of strings, optional title that would be a nested structure. So in protocol buffers, we can define some classes just like in Java or C++, and so on, right? So you would have absolutely no problem learning Parquet, protocol buffers, now that you're equipped with the general knowledge, right? So that's my last slide for the data modeling and validation. This idea that we are now in a situation that we're able to store data even if it's a huge mess. Even if it's not valid, if it's just a huge collection of totally unrelated JSON documents with plenty of keys and domains that don't match, we can break domain integrity, we can break relational integrity, we can break atomic integrity and store all of that data. That's the first thing. That we could not do with relational databases or CSV. However, even though we do have that freedom and that luxury to store messy data, we still have the option to introduce schemas and to enforce some structures on the data and to enforce specific types, specific structures that say certain objects should have specific keys with specific types, that certain XML elements must have specific child elements, specific attributes with specific types. And if your schema is well specified, that you really specify a type for every kind of key, you don't allow for unknown keys and so on, then you get something that is more or less homogeneous. Then you can fit it in a data frame, and then you can save it in a format like Parquet that is much smaller in space on disk and much faster to read than JSON. All right? So that's the end of this one. Who has any questions? Anything you want to know? Yes? So that I wouldn't know. That would be the very specifics of dates. So I don't know if there is a difference, but what I can tell you is just looking at the documentation, it's possible to figure it out, right? Because this here is exactly what I meant with the fact that it might be different from technology to technology. Some may have microseconds, some may have nanoseconds, but it's easy because you just need to look at the documentation. And maybe Avro has yet another way of doing that, and the protocol buffers and so on, they each have their own. But what I want you is to have this holistic view, to understand, have this generic knowledge of the landscape in such a way that it's very easy for you to learn any of these formats and schema languages. Right? I was about to say, did I answer your question? But no, I did not, because I don't know about the nanoseconds, right? But I know we could look at it. It's actually one of the interesting things that happened with the internet in the way that our brains were actually modified. Because before the internet, we had more to learn things by heart. And what happened with the internet is that we modified our brain plasticity in a way that we no longer necessarily remember things, but we remember where things are, where things can be looked up. So you might not know certain things, but you know the Wikipedia page that you need to look at in order to find out where it is. So it's very interesting what's happening to the way that we think. Right? All right, any other questions?
Yes, there's a question on Zoom. So the question is, so in order to save something to Parquet, are the key conditions first that there's a schema, second, the document is well formed, and third, that it's valid against the schema? Or are there additional
What was
conditions?
the first condition? So well formed and valid I got, but the first one?
Just have a schema to check validity.
Yes. Mm-hmm. Yes, indeed. If you want to save a document as Parquet, a prerequisite for that is to come up with a schema and to have data that is valid against that schema. That is a prerequisite. You can do it as an exercise. I think there's maybe even an optional exercise on that. If you take specifically the great language game that has these 16 million objects that all look alike, this is very easy to do a schema against. I even gave you the schema last week. And when you have a schema, then you can take the data, validate it against the data frame, and save it as Parquet, in the Parquet format. Now, that's how it works with the great language game, because that one is easy. And then there is the real life that makes it more difficult, because in the real life, you might download some data set from the internet, and then you try to build a schema. First, you realize it may be not so simple because there are so many keys and so much structure. And then you realize that the objects look alike, but if you go 10 years ago, they were not like this. And so you see that every couple of years, there's a change in the structure. This is the real life, right? And so in that case, there is a bit more work. It's not just about validating the data because the data might not be valid or the schema has changed over time. And so here you need to fix things a little bit. You need to transform the data to make it valid against the schema, and then you can save the schema. And that is also the daily life of data engineers and data scientists, that they take data, they fix it, give it some structure, and then save it in a specific format, right? So it's a very common thing to do. How do you do that? Well, we'll see in a couple of weeks with query languages that there are ways. You can use Python, of course, but there are also query languages that allow you to transform the data in this way, right?
So maybe one component of the question, well-formedness, is obvious, is necessary?
Yes, so to answer the rest of the question, yes, absolutely. Your data needs to be well-formed, because if you have a data that you download and it's not even well-formed, then what can you do with it, right? So of course you could attempt to fix it, but good luck with that, right? If you have, it's going to be a nightmare, especially if you have billions of lines and it's not well-formed, that might be very, very complicated. So yes, absolutely, it must be well-formed. And it must be valid, or you need to fix it in such a way that it becomes valid. That's how I would put it. Right? Yes? Did it answer the question?
I think it did. There was just a follow-up question.
Oh, there's a follow-up question. Maybe I'll go to you and then I go to the follow-up question.
Yeah.
Right? Yes, absolutely. Validity implies well-formedness. I could also formulate it as, if the data is not well-formed, then it doesn't make any sense to ask if it's valid, right? It's a prerequisite for asking for validity. Yeah. And well-formedness is kind of the fundamental, right? If the data is not well-formed and you cannot read the file, then you cannot go very far. Yeah. So absolutely, you're correct. Yeah.
So the follow-up question is, okay, before we saw that we need validity against the schema. Now the follow-up question is, but don't we additionally need that this schema can't be represented as a data frame?
Yes, so now this is, I'll comment on that. Yes, absolutely. The notion of a schema is very broad. It also depends on the language. There are things, most of the things you can do with JSON schema, XML schema, they all allow you to do that. Then if you look into the details, you might find out that some languages are more powerful for certain things and less for others. And so it might be that you can do some constraints in a schema language that you cannot do with another schema language, right? So there's a lot of things that you can enforce in a schema. In fact, if you're a mathematician, you could basically say yes, but you can also define a schema that doesn't enforce anything, right? You can just say, okay, my schema is that the object must be an object. And yes, mathematically, you're absolutely correct. You can absolutely do that. In JSON, for example, you can just specify a schema that doesn't have any key, and you make it open, saying that any key can happen, and that's it. And then you allow for any object. So technically speaking, you could have a schema so that everything is valid against that schema. But of course, you cannot turn it into a data frame. And it is true that in order to be able to create a data frame, you must be able to create a data frame schema. And a data frame schema requires to know the columns in advance. You have to specify exactly the columns you have without any extra columns or extra keys. Data frame types must be concrete. What I mean with that is you can say that's a string, that's an integer, that's an array of dates, and so on. You cannot have a type that just says object. That's just an object, right? At least in the earlier generations of data frames. But data frames still have some flexibility. For example, in a data frame, values can be optional. So it's totally fine if in your JSON schema, you have a key that's optional. In a data frame, it's fine if it's absent. In a data frame, you just put a null in there, and then data frames support nulls, right? So it is true, to answer your question, that yes, the schemas must still not be too exotic. They should have concrete types and no open object types. Yeah. I would like to add something, but I don't want just before the break, but I forget it if it's too confusing. I said earlier generations of data frames because there is a newer generation of data frames that now is appearing, and even in Spark recently they started introducing that. It's variant types. Is that in newer generations of data frame, it is possible to have a column that doesn't have any type, that basically says in that column you can have anything, and they call that variant. But within the theoretical framework I've given you, that's easy. They just break domain integrity, right? That's all it does. So the newer generations of data frames are also able to break domain integrity. That's essentially what's going on, right? So it gives you more flexibility. Okay. Let's take a break. 15 minutes. If you have more questions, I'll take the time to answer questions, and then I'll start with MapReduce, actually querying data. Right. So see you in 15 minutes.